This week we'll study interference and diffraction. In this lab, we will measure the wavelength of laser light in two ways, by inspecting a single-slit diffraction pattern and by inspecting a double-slit interference pattern. In the single-slit case, we'll shine a laser on a slit of known slit width, A, and observe the diffraction pattern on a screen. The locations of the minima in intensity are described by the equation A sine theta equals m lambda. In the double slit case, we will shine a laser on a double slit of known slit separation D and observe the diffraction pattern on a screen. The separation of the peaks of highest intensity are described by the equation D sine theta equals m lambda. Our equipment this week consists of a laser on one end of a track with distance markings. At the other end is a light detector that can move back and forth perpendicular to the track. Before you make any measurements, you'll line the laser light up so that the laser beam is at the same height as the openings in the detector. You'll do this by turning the alignment screws on the back of the laser. Our diffracting element will be selected from a circular wheel with different sets of multiple slits in their surfaces. The slit separations and widths are written on the wheels. There's one wheel for multiple slits and another for single slits. To set up one of the slit wheels, just snap it in place in the tracks right in front of the laser. You want the distance from the slits to the detector to be about 1 meter. Now if you look at the detector, you'll see you have a diffraction pattern with bright and dark regions. To measure the intensity across the pattern, you'll rotate the wheel on the back of the detector to slide it back and forth. The instructions to connect the detector to a Pasco box to record the pattern in Data Studio is in the lab manual. By measuring the distance between the peaks in Data Studio, you'll be able to calculate the wavelength of the laser light.